Hello everyone, welcome back to my channel. One of the greatest drawbacks of using the Python programming language is the fact that it is single-threaded. Today I'm going to show you how you can overcome this limitation using a Python package called Dask. Dask is a flexible library for parallel computing in Python. If we take a look at the GitHub, it has 6,855 stars. You can help this by clicking the star button there. The main contributor to the Dask project is Matthew Rocklin, who was working at Anaconda during a bulk of the development of Dask. Dask is very well integrated into the entire scientific Python ecosystem, and it has built-in support for scaling data structures like NumPy arrays and pandas data frames. The Dask APIs for these data structures are a subset of the original data structures APIs. So if you scale your NumPy arrays using Dask, you can work with those arrays in the same way that you would expect to work with a NumPy array. Today I'm going to be showing you one of the core modules of Dask known as Dask Distributed. Dask Distributed is a lightweight library for distributed computing in Python. This is the part of the code that allows Dask to scale beyond a single process. And the benefit of using Dask Distributed over a built-in module like multiprocessing is that you can scale your Python code beyond a single machine. Let's jump into the code and I'll show you how simple it is to scale out your Python code. The first thing that you're going to want to do is install Distributed. I'm working in a Conda environment here and I already have pip installed. So I'm going to run pip install distributed. Next, we are going to import a client from the distributed library. If we want to run parallel Python across all of the cores on our machine, then we are going to use a local cluster. This is the cluster that is used by default. So if I instantiate a client and print the client, we should be able to see some information about the client and the cluster. But there's an error that is thrown and it's a little bit difficult to figure out what exactly this error means. So I'm going to tell you. Dask wants us to run this code under an if name equals main statement here. And now this code should run. Our current client is connected to a cluster that has 4 processes, 12 threads, and memory of 33.3 gigabytes. This is also the port of the scheduler. When I'm writing code using distributed, I like to explicitly instantiate my cluster object, and then we can just pass in the cluster into the client. And notice that if we are running this code across a Dask cluster that is not on our local machine, it's a remote Dask cluster, then we still use the same process for connecting to the cluster. We just need to pass in the scheduler IP address into the client. Now we have our client and our cluster object. I'm going to show you how we can start submitting Python code to our cluster. I'm going to make 3 functions. Each function is going to represent some work that is being done. The functions vary based on the difficulty of completing them. So it's a way of simulating some work that is being done. We have complex, which takes 10 seconds, hard, which takes 5 seconds, easy, which just takes 1 second. And for a later example, we can have single task that takes some variable amount of time X. The way that our client is going to communicate with the cluster is with remote function calls that are going to return a future object. This future object just simply represents some work that is going to be completed. But the future is not going to contain the result when it is returned. Let me show you an example. We can submit a function to the cluster by calling client.submit and passing in the function object. So we'll pass in hard. We're not going to call the function. We're going to pass in the function as an object. We can then also pass in any arguments to the function, but in this case, there aren't any arguments that are taken. So we just need to pass in hard, and this is going to return a future. Notice in our function that we are printing out the name of the function. So if we run this code, we should expect to see that print statement here because our cluster is on our local machine. So everything is happening within this machine. Let's try running this code and seeing what happens. It doesn't print anything. Let's try printing out the future object that is returned. So we can see some information about the future object. It has a key and also it has a state. It is in a pending state at the moment. Our code here is running and immediately this client.submit is returning a future and the future state is pending. Once the code has completed executing, the local process is terminated, which means that our local cluster is also terminated because we are instantiating it within this process here. In order to get the result of this future, we need some way of waiting on the future to complete. To do that, we are going to call a method on this future object, future.result, and we will print the result of this future object. Now let's try running this code. Now we are printing out hard twice, once within the function itself, and also we are printing out the result that is returned, which is the same thing, hard. That's how you submit work to be done by the cluster. Let's try another example where we are submitting multiple functions to the cluster. So we're submitting hard and easy, and we are waiting on the hard function to complete. Easy completes right away. It only takes 1 second, but we don't print the result of easy. So we only see easy once from within the function call, and then we see our hard 2 times. There's another very useful function within the distributed library called AsCompleted. To illustrate how AsCompleted works, we are going to submit each function a certain number of times, collect all of the futures from each one of those submitted function calls, and then we are going to wait on all of the futures that are returned. And what AsCompleted is going to allow us to do is collect the results of the futures as they complete, and then we can do something with those results as they are returned. Okay, so we are iterating through this 3 times, and we are going to submit each one of our functions, and we are going to collect the future within a list called futures. And then outside of this for loop, we will call AsCompleted on the futures, and then we will have a second for loop, for I in completed. Completed is a generator and it will return each one of the results as they are completed. If we try to run this function here, we're going to see some unique behavior. We would expect to see each one of our functions executed 3 times, but instead we're just seeing each one once. If we dive into the code a little bit with our debugger, on the first iteration our futures are added. On the second iteration, the second round of futures are added. If we look into these futures for our 2 easy functions, they both have the same key. And this is because by default, distributed is creating a key from the name of the function and a hash that is generated. So if we want this code to work, we're going to have to add in our own custom key. And now we are getting the behavior that we would expect. Dask is going to compute these functions based on the order in which they are received. If we switch up the order a little bit and rerun this code, we get the same exact result. And this is because the number of processes and the number of threads within our cluster. But if we increase the number of iterations, we will start to see these easy functions not all completing first. The order in which these tasks are received is going to become an important factor. We can get more fine-tuned control over which tasks are completed first by setting the priority of the tasks that are submitted. Let's try setting the priority of the easy tasks to 10. The higher the priority is, the more likely the workers are going to be to execute those tasks first. So we can see in this case where we set the priority for the easy task, they are all completed first, even though they're submitted last in our iterations here. Another important thing to know is, what if we submit a task, but we aren't going to keep track of the future in our local environment? So in this case, I took away the reference to the future that is returned from this client.submit, and then I don't add that future to our futures list. Let's see what happens when I run this code. When I run this code, it looks like one of the easies slipped by and got executed. It was printed, but none of the other easy functions were executed by the scheduler. And this is because if there's no reference to a future, then the future is not going to be executed. This saves on a lot of unnecessary work for the scheduler. But if you do want a task to be executed and you don't care about the future, then there's a function to allow you to do that. It is called Fireandforget. Forget. So now let's try doing the same thing here. In order for Fire and Forget to work, we do need the reference to the future, and I will just execute this to show how the behavior is when I have that reference. Easy does get executed a little bit more often, but because we aren't adding this future object to our futures and keeping track of it, we aren't seeing all 30 of the easies being executed. So far there are just 4, and that's all we're going to see. So what if we want all of these futures to be executed? So we are going to run Fire and Forget, and we are going to pass in our future object. Fire and Forget is going to make sure that the task is executed at least once. So now these easy tasks are being completed much more often. I took away the priority, so it's being completed as it was in the first example. One other parameter to the submit function that you should know about is retries, where you can pass in an integer, and if your task fails, Dask will retry that task multiple times. Also, you do have control over what worker the task is submitted to. So you can actually pass in a list of worker names or host names for the workers that you want your task to be submitted on. So imagine you're going to train a deep learning model with one of your tasks, and you want that task to go to a machine with a GPU. Well, you can tell Dask which worker to send that task to. The way I am executing functions on the cluster is with this submit method, but there's also a map method that you can use. For the map method, we can use our variable time task. So we'll pass in the task function. You can pass in any function here. We are also going to pass in an iterable, and we are going to execute that function on every value within that iterable. Client.map is going to return a list of futures. And then we are going to call a method on our client object called gather. We're going to pass in our futures, and this is just another way of waiting for futures to complete. Everything that I just showed you is scaling Python on a single machine. We are controlling multiple processes within our local environment, and by default we are creating a process per core on our machine. I'm still going to be working on my local machine, but I will show you what it's like to work with Dask on a remote cluster. I will use Kubernetes to launch a Dask cluster, but I'm going to do this on my local environment using Minikube. The process will be very similar though if you're running Kubernetes in the cloud. And also it's very similar if you're running Dask on an HPC system or one of the many other types of clusters that Dask has support for. Just to quickly show you the types of systems that Dask has support for, Dask has a sub package called Dask Job Queue, and this module here is for HPC systems. This example is PBS cluster. There's also Slurm, LSF, and a few of the other well-known HPC systems. There's also the Dask Kubernetes module and Dask Yarn if you want to spin Dask up on a Hadoop-based system or other Yarn clusters. All right, so the first thing I'm going to do is just start up Minikube. All right, on my machine, I already have a Dask cluster up and running on Minikube. Dask has a Helm chart available for setting up a Dask cluster online, and there's a bunch of resources. I will link to those in the description below. The main point that I want to show is how to connect to an external cluster. In our client, we want to pass in the address. Let's just print our client for starters and see if this works. We also need our port number, so 8786. I was having some technical difficulties there for a moment, but I was able to connect. You'll get this message here if any of your packages are different from your local environment and your remote environment. And those are some of the complexities that you're going to have to deal with when working with a remote cluster. You need your local environment to be the same as the remote environment that you're working on. So managing the packages can be very challenging and something that you're going to have to deal with if you want the benefits of scaling out your Python processes to a large remote cluster. Let's try computing our futures like we did before. I need to install some of these missing libraries because I'm having some deserialization errors come up. All right, I'm still getting this error, and I realize what the problem is. I'm using Python 3.7, and on the Dask cluster, it's Python 3.8, and that's where the serialization error is happening. Okay, so I switched my environment over to a Python 3.8 environment, and I ran the same code, and notice how this time we aren't seeing those print statements, and that's because the code is being executed on our remote cluster. This time I iterated through the results and I printed each result, and in our task function we are returning the X parameter that we passed in, so we get 0 through 9 here. And that is it. That is your basic introduction to Dask Distributed and how to scale out your Python code across multiple cores on a single machine and across multiple computers within a distributed computing environment. With Dask Distributed, you can control hundreds or even thousands of Python processes and use all of those Python processes to execute your code, make your code run faster, make your code run in parallel, and in general, just scale out your Python code. Thanks for tuning in. Be sure to subscribe to this channel, like the video, and I will see you next time.